In the context of wiring an airport hangar, several questions arise concerning the National Electrical Code, specifically regarding low-voltage wiring, cable types, and hazardous locations. Firstly, the question of whether low-voltage wiring must be in conduit is addressed. The National Electrical Code does not explicitly mandate that low-voltage wiring be enclosed in conduit in all scenarios. However, it is crucial to refer to Article 725.50a, which stipulates that low-voltage systems must be installed in a manner that adequately protects the conductors from physical damage. This implies that even if conduit is not strictly required, the installation method must ensure the wiring's integrity against potential harm. Secondly, the inquiry about TC cable arises from Section 513.7, which pertains to wiring methods in aircraft hangars. TC cable stands for Type TC tray cable. This is a factory-assembled cable consisting of insulated conductors, with or without associated bare or covered grounding conductors under a metallic sheath or having a thermoset or thermoplastic jacket. It is designed specifically for use in cable trays or raceways. The National Electrical Code recognizes it for use in industrial settings, power, control, signaling, and communications circuits. The third question delves into the concept of nonincendive field wiring, particularly within the context of Article 501.10. B3. Nonincendive field wiring refers to wiring that, under normal operating conditions, is incapable of causing ignition in a specified hazardous atmosphere. This type of wiring is commonly employed in Class 1, Division 2 hazardous locations, where flammable gases, vapors, or liquids may be present but are not expected to exist under normal operating conditions. Non-incendive circuits are designed to limit the energy available to a level that is insufficient to ignite the hazardous material. Moving on, there's a query regarding the applicability of Article 725.11. B to the situation involving garage door openers in the hangar. Article 725.11. B addresses scenarios where damage to remote control circuits of safety control equipment could introduce a hazard. In such cases, the conductors of these remote control circuits must be installed in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, electrical metallic tubing, type mineral insulated cable, type metal clad cable, or be otherwise suitably protected from physical damage. However, a standard garage door opener is generally not classified as safety control equipment within the context of this code section, so Article 725.11. B would not be applicable in this particular situation. Finally, the ultimate question revolves around whether the low-voltage wiring needs to be in a protective raceway or if the current installation, lacking such protection, is acceptable. While the National Electrical Code does not explicitly demand conduit, the overarching requirement is to protect the wiring from physical damage, as emphasized in Article 725.50. An electrical inspector may express concern if the wiring is exposed and susceptible to damage. Therefore, it is essential to provide adequate protection. In light of these considerations, a prudent recommendation would be to install the low-voltage wiring in a protective raceway. Options include flexible metal conduit or surface-mounted raceway. This measure ensures that the wiring is shielded from potential physical damage and aligns with the intent of the National Electrical Code. Doing so can proactively address the inspector's concerns and facilitate a smoother approval process. It is important to note that interpretations of the National Electrical Code can vary and local amendments may exist. Therefore, engaging in open communication with the local electrical inspector and seeking clarification on any specific requirements or concerns is always advisable. Furthermore, consulting with a qualified electrical engineer or licensed electrician can provide valuable insights and ensure compliance with all applicable codes and regulations. Understanding cable types is crucial for proper electrical installations. Type NEC cable, or metal-clad cable, is a factory-assembled cable containing one or more insulated conductors enclosed in a metallic sheath of interlocking tape, or a smooth or corrugated metallic tube. Type NEC cable is permitted for services, feeders, and branch circuits, and it can be used for power, lighting, control, and signal circuits. Type MI cable, or mineral insulated cable, is a factory assembly of one or more conductors insulated with a highly compressed refractory mineral insulation and enclosed in a liquid-tight and gas-tight metallic sheath. Type MI cable is suitable for use in hazardous locations, corrosive environments, and high-temperature applications. Understanding hazardous locations is another key aspect of electrical safety. Class 1 locations are those where flammable gases or vapors are or may be present in the air in quantities sufficient to produce explosive or ignitable mixtures. Class 1 locations are further divided into Division 1 and Division 2. A Class 1, Division 1 location is one in which ignitable concentrations of flammable gases or vapors exist continuously, intermittently, or periodically under normal operating conditions. A Class 1, Division 2 location is one in which ignitable concentrations of flammable gases or vapors are not likely to exist under normal operating conditions. Article 500 of the National Electrical Code provides detailed requirements for electrical equipment and wiring in hazardous locations. Equipment used in hazardous locations must be specifically designed and approved for the class and division of the location. This ensures that the equipment will not cause an ignition of the flammable gases or vapors that may be present. When installing electrical wiring in an airport hangar, it is essential to carefully consider the presence of flammable materials such as aviation fuel and other solvents. The hangar must be properly classified according to the National Electrical Code, and all electrical equipment and wiring must comply with the requirements for the specific class and division of the location. Proper grounding is also critical for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to trip circuit breakers or fuses and prevent electrical shock hazards. All electrical equipment and wiring must be properly grounded in accordance with Article 250 of the National Electrical Code. In addition to the specific code requirements, there are also several best practices that should be followed when installing electrical wiring. Always use the correct size and type of wire for the application. Make sure all connections are tight and secure. Protect wiring from physical damage. Label all circuits clearly. And always test the insulation before energizing it. Low voltage wiring systems, often utilized for control, signaling, or communication purposes, operate at voltage levels significantly lower than standard power distribution systems. Understanding the nuances of these systems is crucial for safe and effective installation. Firstly, identifying the specific type of low voltage system is paramount. Common types include Class 1, Class 2, and Class 3 circuits, each with distinct characteristics and limitations defined by the National Electrical Code Article 725. Class 1 circuits typically operate at up to 30 volts alternating current or 60 volts direct current and may carry higher energy levels, necessitating careful overcurrent protection. Class 2 and Class 3 circuits, on the other hand, are power limited, reducing the risk of electrical shock and fire hazards. Secondly, selecting the appropriate wiring method is critical. The National Electrical Code dictates permissible wiring methods based on the circuit class and the installation environment. For Class 1 circuits, wiring methods resembling those used for standard power circuits are generally permitted, such as conductors and conduit or cable assemblies. However, for Class 2 and Class 3 circuits, specific cable types like CL2 or CL3 rated cables are often required to ensure adequate insulation and fire resistance. Thirdly, proper overcurrent protection is essential for Class 1 circuits to prevent overheating and potential fire hazards. Overcurrent protection devices, such as circuit breakers or fuses, must be sized appropriately to protect the conductors from excessive current flow. For Class 2 and Class 3 circuits, power supplies are typically designed with inherent current limiting characteristics, eliminating the need for separate overcurrent protection devices. Fourthly, separation from power circuits is crucial to minimize the risk of interference and ensure the integrity of low voltage signals. The National Electrical Code mandates that low voltage wiring be separated from power circuits by a specified distance or by a physical barrier such as conduit or raceway. This separation prevents inductive coupling and reduces the likelihood of voltage transients that could damage sensitive electronic equipment. Fifthly, proper termination and splicing techniques are essential for maintaining reliable connections. Terminations must be made using approved connectors or terminals, and splices should be avoided whenever possible. If splices are necessary, they must be made in accessible locations using approved splicing methods, such as crimp connectors or wire nuts. Sixthly, grounding requirements must be carefully considered, particularly for Class 1 circuits. Grounding helps to minimize electrical noise and provides a path for fault current to flow back to the source, reducing the risk of electrical shock hazards. The National Electrical Code specifies grounding requirements for different types of low-voltage systems, depending on the application. Seventhly, labeling and identification are essential for facilitating troubleshooting and maintenance. All low-voltage wiring should be clearly labeled with its circuit designation and voltage rating. This helps to prevent accidental connections to the wrong circuits and simplifies the process of identifying and resolving problems. Eighthly, compliance with applicable codes and standards is paramount. Low-voltage wiring installations must comply with all relevant requirements of the National Electrical Code, as well as any local codes or regulations. It is essential to consult with a qualified electrical inspector or engineer to ensure that the installation meets all applicable requirements. Ninthly, special considerations may apply in certain environments, such as hazardous locations or areas with high levels of electromagnetic interference. In these cases, additional precautions may be necessary to ensure the safety and reliability of the low-voltage wiring system. Tenthly, regular inspection and maintenance are essential for ensuring the continued safe and reliable operation of low-voltage wiring systems. Inspections should be conducted periodically to check for signs of damage, deterioration, or loose connections. Any problems should be addressed promptly to prevent potential hazards or malfunctions. Voltage drop calculations are a fundamental aspect of electrical engineering, crucial for ensuring efficient and safe operation of electrical circuits. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its impedance, which is the opposition to the flow of alternating current. Excessive voltage drop can lead to a variety of problems, including reduced equipment performance, overheating of conductors, and even equipment failure. Firstly, understanding the factors that influence voltage drop is essential. The primary factors are the conductor's resistance, the length of the conductor, and the amount of current flowing through the conductor. The resistance of a conductor depends on its material, size, and temperature. Longer conductors have higher resistance, and higher current flow results in greater voltage drop. Secondly, calculating voltage drop involves using Ohm's law and other relevant formulas. The basic formula for voltage drop is voltage drop equals current times resistance. However, for alternating current circuits, impedance must be considered instead of just resistance. Impedance includes both resistance and reactance, which is the opposition to current flow due to inductance and capacitance. Thirdly, the National Electrical Code provides guidelines for acceptable voltage drop limits. The National Electrical Code recommends that voltage drop on feeder circuits should not exceed 3%, and the total voltage drop on both feeder and branch circuits should not exceed 5%. These limits are intended to ensure that equipment operates within its rated voltage range and to prevent overheating of conductors. Fourthly, selecting the appropriate conductor size is crucial for minimizing voltage drop. Larger conductors have lower resistance and therefore result in less voltage drop. Voltage drop calculations should be performed to determine the minimum conductor size required to meet the National Electrical Code's voltage drop limits. Fifthly, using conductors with lower resistance materials, such as copper instead of aluminum, can help to reduce voltage drop. Copper has a lower resistivity than aluminum, meaning that it offers less resistance to current flow. However, copper is also more expensive than aluminum, so a cost-benefit analysis should be performed to determine the most appropriate conductor material. Sixthly, reducing the length of conductors can significantly reduce voltage drop. This can be achieved by locating equipment closer to the power source or by using multiple power sources to distribute the load more evenly. Seventhly, increasing the voltage level of the circuit can also reduce voltage drop. For a given amount of power, higher voltage circuits require less current, which results in lower voltage drop. However, increasing the voltage level may require the use of different equipment and may also pose additional safety hazards. Eighthly, using parallel conductors can help to reduce voltage drop. Parallel conductors effectively increase the cross-sectional area of the conductor, which reduces its resistance. However, parallel conductors must be properly sized and installed to ensure that they share the load equally. Ninthly, power factor correction can help to reduce voltage drop in alternating current circuits. Power factor is a measure of how effectively electrical power is being used. Low power factor can result in increased current flow and therefore increased voltage drop. Power factor correction devices, such as capacitors, can be used to improve the power factor and reduce voltage drop. Tenthly, regular monitoring and maintenance of electrical circuits can help to identify and address voltage drop problems before they become severe. Voltage measurements should be taken periodically to check for excessive voltage drop. If voltage drop is found to be excessive, corrective action should be taken to address the problem. In the realm of electrical installations, understanding the proper application and handling of flexible metal conduit, often referred to as FMC, is paramount. Flexible metal conduit serves as a protective raceway for electrical conductors, offering versatility and ease of installation in various environments. Firstly, identifying the different types of flexible metal conduit is essential. Standard flexible metal conduit is constructed from a helically wound strip of metal providing flexibility while maintaining structural integrity. Liquid-type flexible metal conduit, often abbreviated as LFMC, incorporates a liquid-tight jacket, making it suitable for wet or damp locations. Secondly, determining the appropriate size of flexible metal conduit is crucial. The size of the conduit must be sufficient to accommodate the number and size of conductors being installed, while also adhering to the fill requirements specified in the National Electrical Code. Overfilling the conduit can lead to overheating and potential damage to the conductors. Thirdly, selecting the correct fittings is essential for ensuring secure and reliable connections. Fittings designed specifically for flexible metal conduit must be used to connect the conduit to electrical boxes, enclosures, and other equipment. These fittings provide mechanical support and electrical continuity. Fourthly, proper installation techniques are necessary for maintaining the integrity of the flexible metal conduit system. The conduit should be securely supported at regular intervals, typically every 3 to 4 feet, to prevent sagging or damage. Ends in the conduit should be made gradually to avoid kinking or reducing the internal diameter. Fifthly, grounding requirements must be carefully considered. Flexible metal conduit can serve as an equipment grounding conductor under certain conditions, as specified in the National Electrical Code. However, supplemental grounding conductors may be required in some cases to ensure adequate grounding performance. Sixthly, protection from physical damage is essential. While flexible metal conduit provides a degree of protection to the conductors, it is not impervious to damage. In areas where the conduit is exposed to physical abuse, additional protection measures, such as conduit guards or enclosures, may be necessary. Seventhly, liquid-tight connections are crucial for liquid-tight flexible metal conduit. When using liquid-tight flexible metal conduit, it is essential to ensure that all connections are properly sealed to prevent moisture from entering the conduit system. This can be achieved by using liquid-tight fittings and applying sealant or tape as necessary. Eighthly, compliance with applicable codes and standards is paramount. Flexible metal conduit installations must comply with all relevant requirements of the National Electrical Code, as well as any local codes or regulations. It is essential to consult with a qualified electrical inspector or engineer to ensure that the installation meets all applicable requirements. Ninthly, special considerations may apply in certain environments, such as hazardous locations or areas with high levels of electromagnetic interference. In these cases, additional precautions may be necessary to ensure the safety and reliability of the flexible metal conduit system. Tenthly, regular inspection and maintenance are essential for ensuring the continued safe and reliable operation of flexible metal conduit systems. Inspections should be conducted periodically to check for signs of damage, deterioration, or loose connections. Any problems should be addressed promptly to prevent potential hazards or malfunctions. Ensuring that electrical installations are performed correctly and in accordance with the National Electrical Code is a critical responsibility for electrical professionals. The National Electrical Code, published by the National Fire Protection Association, provides comprehensive guidelines for safe electrical practices, covering a wide range of topics from wiring methods to equipment installation. Firstly, understanding the scope and purpose of the National Electrical Code is essential. The National Electrical Code is intended to safeguard persons and property from hazards arising from the use of electricity. It is not a design manual, but rather a set of minimum requirements that must be met to ensure electrical safety. Secondly, staying up to date with the latest edition of the National Electrical Code is crucial. The National Electrical Code is revised and updated every 3 years to reflect changes in technology, industry practices, and safety standards. Electrical professionals should familiarize themselves with the latest edition of the National Electrical Code and any local amendments that may be in effect. Thirdly, obtaining proper training and certification is essential for demonstrating competence in electrical work. Many jurisdictions require electricians to be licensed or certified, which typically involves completing an apprenticeship program and passing an examination. Ongoing training and education are also important for staying abreast of changes in the National Electrical Code and best practices. Fourthly, carefully reviewing the project plans and specifications is crucial before beginning any electrical work. The plans and specifications provide detailed information about the electrical system, including the location of equipment, wiring methods, and circuit requirements. Any discrepancies or ambiguities should be clarified before proceeding with the installation. Fifthly, selecting the appropriate materials and equipment is essential for ensuring a safe and reliable electrical system. All materials and equipment must be listed or labeled by a recognized testing laboratory, such as Underwriters Laboratories, to ensure that they meet applicable safety standards. The materials and equipment must also be suitable for the specific application and environment. Sixthly, following proper wiring methods is critical for preventing electrical hazards. The National Electrical Code specifies detailed requirements for wiring methods, including conductor sizing, insulation types, and raceway systems. All wiring must be installed in accordance with these requirements to prevent overheating, short circuits, and other potential problems. Seventhly, properly grounding and bonding the electrical system is essential for minimizing the risk of electrical shock. Grounding provides a path for fault current to flow back to the source, which helps to trip circuit breakers or fuses and prevent electrical shock hazards. Bonding ensures that all metal parts of the electrical system are electrically connected, reducing the potential for voltage differences that could cause shock. Eighthly, testing and inspecting the electrical installation is crucial before energizing the system. Testing verifies that the electrical system is functioning properly and that all connections are tight and secure. Inspection ensures that the installation complies with the National Electrical Code and other applicable requirements. Ninthly, documenting the electrical installation is essential for future maintenance and troubleshooting. Accurate records should be kept of the electrical system, including wiring diagrams, equipment schedules, and test results. This documentation can be invaluable for identifying and resolving problems that may arise in the future. Tenthly, continuous learning and improvement are essential for electrical professionals. The electrical industry is constantly evolving, with new technologies and practices emerging all the time. Electrical professionals should stay informed about these developments and seek opportunities to expand their knowledge and skills. In summary, the considerations regarding low-voltage wiring in an airport hangar environment necessitates careful attention to the National Electrical Code, particularly concerning physical protection, cable selection, and adherence to hazardous location classifications. A proactive approach, involving clear communication with electrical inspectors and qualified professionals, ensures a compliant and safe installation.